In this lesson, we're going to look at an example of a two-tailed hypothesis test for proportions. Let's illustrate this with an example. Advances in medical care, such as prenatal ultrasound examination, now make it possible to determine a child's sex early in pregnancy. There is fear that in some cultures, some parents may use this technology to select the sex of their children. A study from Punjab, India reports that in 1993, in one hospital, 56.9% of the 550 live births that year were boys. It's a medical fact that male babies are slightly more common than female babies. The study's authors report a baseline for this region of 51.7 male live births. Is there evidence that the proportion of male births has changed? So let's first address this idea of, is there some evidence? Well, in general, in the region, 0.517 are male live births. But in this particular hospital, there seems to be more, 56.9%. So we have some evidence, but we need to run a hypothesis test to determine if this is convincing statistical evidence to find for the alternative. So we're going to go through our state plan do conclude, and I'm going to be zooming in and out so you can see the problem all at once on your screen, but that means when I'm zoomed out, of course, the writing will be very small. So let's go into our state portion. So when I state, this is where I'm going to state my hypothesis as well as any parameters. So I begin by saying that we want to perform a significance test where the null, so now I'm going to state my null with a colon. I'm talking about proportions, so make sure you use the parameter. And I'm assuming that it's equal to 0.517, the general rate there in the region. Now my alternative would be that it is somehow different, that it's not equal to 0.517. And I'm going to state now what P represents. So I'm going to say where P is the true proportion, now I'm talking about my parameters, so what my population is, of male live births in Punjab, India. It's not the whole world, it's just that region. And I'm going to state my alpha level, where we will use an alpha equals 0.05 significance level. Now it's difficult in this software for me to write alpha, but you can, of course, write your Greek letter that looks like this, alpha equals 0.05. We're ready to move on to our plan, which is where we're going to address our conditions, and we will name our significance test. So I'm stating that if conditions are met, we will do a one proportion Z test, and now I'm going to specifically state my three conditions. So my first one is random. And now this is where I need to be a little bit cautious, because I don't think I can just jump right in and say that my births are random. So if this would happen to you on the AP exam, you would still continue with your significance test, okay? But you're going to make a statement of caution. So I've stated that the 550 births are not at random. So I must be cautious about generalizations to the population. But then I'm going to say, I hope that this is a representative year, and I think that the births at this hospital are typical of this area in India. So that's kind of my way of, stating that I recognize that I have an issue with this test. However, I'm assuming that it's representative of the population so that I can still continue. My next condition would be the 10% condition. So I'm going to say that my sample, which is 550 births, is less than 10% of all births in Punjab, India at similar hospitals. Now, we need to address the large counts condition. And just something to be aware of is that you are testing N times P naught, meaning your null hypothesis proportion, okay? A common error is that students will use P hat, which was the 56.9%, but we need to use the 0.517 from our null hypothesis. So I'm stating both n times p naught, which equals 550 times 0.517 equals 284.36, and n times 1 minus p naught, so the expected number of failures, or not male births, both are greater than or equal to 10. We expect at least 10 boys and 10 girls. So I can say that my conditions are met. I'm stating that it's okay to proceed with it. So I've zoomed back out. You can see, of course, now the writing's very small, but I'm moving on to the do part of my test. So this is where I'm going to show my calculations. I'm proceeding with a normal model, so I'm going to sketch my normal model. And I'm going to begin by stating what my sample proportion is, which was p hat, and that was given. It was 0.569. So I'm going to find my z-score. How far from the mean would this sample fall? So to do that, that's 0.569 minus the mean of my distribution, which is my population mean, 0.517 over the standard deviation of my sampling distribution, which would be 0.517 times 1 minus 0.517 over the sample size, which is 550. And going to put that all in the calculator, and I get approximately 2.44. So my null hypothesis is that it differs. So what I'm really doing is I'm considering what's the probability that it is 2.44 standard deviations away from the mean of my distribution or more extreme. So I'm really looking at this area over here, but also this area over here. So this is a two-tailed test. And this is, of course, looking at my standard normal model because I'm doing my z-scores. So I'm going to say that my p-value, because I need to find that, would be equal to the probability that my z-score is greater than or equal to 2.44 or more, so 2.44 or more extreme. But that's really only addressing the right tail of my test, the region over here. So I need to, with a two-tailed test, I'm going to double this. And that means then that I can go to do my calculator, which would be normal CDF. I'm going to end up doing 2 times normal CDF, and you're going to list your lower, upper, mu, and sigma. And when I toss that in the graphing calculator, I get 0.0146. I would encourage you to try this using the one proportion z-test on the calculator as well. If you have a newer model, it can handle the two-tail test. You just select not equal to, and you don't have to double the areas. If you are using table A, definitely make sure you double it. Okay, so let's move on to our conclude portion. So my conclusion is because the p-value equals 0.0146 is less than my alpha level equals 0.05, we reject the null. So when the p-value is low, you reject the h sub o. There is convincing evidence, so now I'm finding for the alternative in context. There is convincing evidence that the proportion of boys born is not equal to its natural level. And then I'm also stating, you know, it appears that the proportion of boys may have increased because I have a sample that's higher. If you're asked to also interpret the p-value, here's just a kind of a general statement. The p-value of 0.146 says that if the true proportion of males is 0.517, then an observed proportion of 0.569 would occur at random only about 1.5% of the time. We're going to now use this same scenario and make a connection to confidence intervals. So it says, are you wondering what the actual proportion P might be for these male births in India? Construct a confidence interval for the proportion of male birth to shed some light on this issue. So I'm stating that we want to construct a 95% confidence interval to capture the true proportion of male births in Punjab. So I'm defining my P here. And then in my plan, this is where I address my conditions. I'm not going to go through all of my conditions again because they are identical to my previous one. So random, I'm not going to address. My 10%, the only difference would be in my large counts condition. Okay, so in the large counts condition, we don't know the value of P, it's what we're trying to find. So I need to check N times P hat, which would be 550 times 0.569, would be equal to 313 males, and N times 1 minus P hat would be, that would make it 237 females, and both are greater than or equal to 10. Okay, so I can proceed with a 1 proportion Z interval, so make sure you name that. And now I'm actually going to construct that 1 proportion Z interval, so that would be in my do section. So I just kind of begin by writing that's equal to P hat plus or minus my Z star times the standard error. Remember, it's standard error because I'm estimating with P hat. So P hat times 1 minus P hat over my sample size. And then I'm going to fill in. So this would be 0.569 plus or minus my Z star for 95 would be 1.96. You can do inverse norm to find that. Standard error, substitute, 0.569, 0.431 for a sample size of 550. Remember the idea that increasing your sample size would of course decrease your margin of error. So let's see, when I do that, I get 0.569 plus or minus 0.041, so that puts my interval at between 0.528 to 0.610. And now I'm going to write my conclusion, stating that I am 95% confident that the interval from 0.528 to 0.610 captures the true proportion of male births in India.